get to the vacuum gauge, so we don't know like how much vacuum is released. Are we supposed to use like the pressure number?
I don't think it asks you to do that.
The lab report said to do that.
Reread the lab report and information. Everything should be clear. Questions?
Is it a micro vacuum distillation?
Micro vacuum distillation? I don't know what the difference is, what micro really means. It will be pretty small.
Because it's the smallest example in like the techniques guide. So it's the smallest example in the techniques guidebook.
I can't hear you. I'm sorry.
It's just the smallest setup for in the technique guide.
It's standard setup you've done before, hopefully. We're just adding a curved adapter and a vacuum line.
For like the same setup for just a simple distillation.
Same setup you've done before, except for adding a curved adapter and a vacuum line. Yeah, not much to it. I'll just tell you then it's distillation. Okay, guys, epoxide chemistry. Any questions? We have a handout today on another handout on alcohol oxidation, including alkene oxidation, which will be our last major topic before the test, and as well as NMR. So the pink goes along with the blue. Any questions about the carbon NMR of the lab from this week? Good to go on that? Any questions about, well, no questions there. Next week we're doing the alcohol diol oxidation, okay, as on the syllabus, yeah? Epoxide chemistry. I think we looked at polymerization last. Synthesis. So there's a variety of things in the back of this handout, including a puzzle worksheet on the epoxides. I gave you one like this on alkenes in Organic 1. You remember? Here's one similar on epoxide chemistry. It has a riddle. Was the sodium atom certain that he had lost an electron? To answer the riddle, you fill in the bottom with correct letter. The letter comes from the correct answer. Okay? It's a good review. We'll look at other things there. Let's see, epoxide reactions, alkyl lithium, we did that one, yeah, Grignard. We did the second one as well, correct? Yeah? Did we do this one with amine, with ammonia?
No.
We got a good nucleophile. Okay, even though it's not an anion, sp3 nitrogen still pretty good nucleophile. Got to have a good nucleophile. We don't have any acid here. You all right? You can't have any acid with ammonia. Ammonia would react with the acid. All right. But epoxides, the oxygen will serve as a leaving group. Where are we going to attack at? Top carbon or bottom carbon?
Bottom carbon.
Bottom carbon, SN2, least sterically hindered, kick off the oxygen. And we get, oh, I see it coming. You see it coming? You don't see it coming. Proton transfer, we'll be doing it a million times this semester. This is going to be like this. The oxygen just opens up. That becomes minus, yeah, that was the leaving group. The ammonia is bonded here. The nitrogen is bonded here. Stereochemistry for the nitrogen. Oxygen's forward, so the nitrogen actually had to come in from the back. Yeah? In, H3, right? We don't magically lose hydrogens, positive charge. Okay, how can we go neutral here? How can we get a neutral product?
Intramolecular proton.
Yes, we don't have to add water.
Back this up.
Proton can come internally. Proton can come from the nitrogen. It needs to get rid of one. Proton transfer, H plus transfer. Okay? H plus transfer. Yes, it's intramolecular, internal. And after proton transfer, we're going to have our product, just a proton is transferred. So the proton now sits on the oxygen, that's OH. And this is going to be what? NH2. Yeah? You got to know what H plus is. If we remove an H plus from here, it's just removing an H. The two electrons stay there as a lone pair. If we just put an H plus here, it just bonds to the one lone pair, okay? There's no electron transfer, it's just the H plus. Question?
Do we not use mechanism arrows to
Yeah,
draw
I was
these?
hoping someone would ask that or we would address that. I'm not going to use it because here it looks like this can just reach down here and take the H and leave the electrons behind. I'm not going to do that there because usually we won't. We'll not do that. It could. It's close enough here that we can show it, but sometimes we'll do proton transfer and it'll be way away from each other. Proton transfer, and I'm talking about it right now, guys, we'll do it a million times. And if you say, well, say, well, we talked about it back then. Remember last Friday, back in January? Yes. It's probably two different molecules. So actually, we lied to them, right?
Intramolecular.
It may actually be two different molecules. That is, you got another molecule up here, okay? And it's got, I'll draw it like this. Well, I'll draw it like this, I think, because the stereochemistry is flipped around. It's probably this. Where does this H come from? It probably comes from this oxygen taking the H from another molecule. And guess what? What takes this H? Not that oxygen, but probably, I think it would be like this. Don't hold me to that stereochemistry. I'm flipping it around. So we got a minus here, and this probably takes the H there. Because you got a million molecules all swimming around to each other, and the O minus of one takes the H from another. Okay? Very often we will, in books, very common, you just say H plus transfer. We're taking care of the proton. I said that 2 weeks ago. We'll always have to take care of the proton. H plus transfer. For me, and on the quiz, you can just say H plus transfer unless something else is required. You don't have to show all this. We will do this a lot. Read about it. Understand what H plus transfer is and how we get the product over there. Now both the oxygen and the nitrogen are both neutral as a result of the H plus transfer. Yeah? In the end, we didn't have to have a workup. See, up here the proton had to come from adding in water or acid. Down here you don't need it. It comes internally. Because the nucleophile sort of provides a proton after it reacts. Because the nucleophile was actually neutral with a proton it could give up, okay? Hopefully you see this. There's your product. Did we get the stereochemistry right? Yes. By the way, one or two above, we actually didn't fully discuss stereochemistry, and someone asked a question about that. I actually gave enantiomers. Do we get the enantiomer here? Plus enantiomer, that compound's chiral. Do we get the enantiomer?
No.
No, we don't get the enantiomer. This is all we get. Common reaction here. Nucleophile, carbon, carbon, OH, yeah? Anybody have a product for this one? Just a two-step reaction. Anybody have a product for it? Anybody have a product for it? How about the one below? Other strong nucleophiles. Anybody have a product for this one?
I do, but I don't know if it's right.
I asked if it was right. I said, anybody have a product for it? What you guess?
You want to come look at it?
Can you name it?
I couldn't. I
Is
don't
it
know
too
about
big?
on the spot.
Well, your mechanism looks right. I don't know about the stereochemistry. Let's look at it and see if we got the stereochemistry right. What's the nucleophile here?
The MEO? Negative?
Your stronger nucleophile is the one that's going to act as a nucleophile. Why would it do nothing but this act as a nucleophile? And why do we use red pens that won't erase? This is just solvent here, okay? MEO minus is your nucleophile. This is going to attack right here, kick off the oxygen. That's going to give OMe, and methyl gets pushed up. And the oxygen over here is straight up. Straight up there, it just opens up. It's still straight up. This is the same over here. There's your product. We just need to put a proton on it. Is that what you got?
I did get stereochemistry right.
You got it right? Okay, that's it. Because the nucleophile comes in, the oxygen's straight up,
Mm-hmm.
so the nucleophile comes in straight down. That methyl is coming forward, but it's also a little bit down. It's got to point down. It's like this. The nucleophile comes in, and the inversion pushes it up. But it's still forward. Okay? There you go. Then put proton. Can the proton come in from the reaction, or do we have to add something?
Add something.
I have something.
Yeah.
It's borderline here. Wayne?
I was going to say the same thing. If it came from the MEOH.
Possibly it could come from the methanol. In practice, you probably still want to add acid here. So it's borderline. We could theoretically just say, okay, methanol can supply a proton. And we can get, I'm just going to show it like that, okay? It becomes OH. The problem is, what does this produce?
Another nucleophile.
Well, it does produce that. Why is that a problem? The problem is, this is an equilibrium, acid-base. Which side's favored?
The right.
Well, see, the problem is they're both alcohols. This is pK of 16, and that's pK of 16. They're both alcohols. Which side's favored?
Neither.
Neither. So you're going to have 50% this and 50% that. We need a stronger acid. So usually in practice, you're probably still going to work this up by adding some stronger acid. Okay? Because this can just take that H and go back. Again, on a quiz test, you may see no workup, and you just have to sort of, okay, how could we go neutral here? But basically, the reaction is pretty much over at this point. Somehow go neutral. We got the most of it here. Attacking the right side, least hindered, stereochemistry is right, yeah. Okay.
Dr. Stevens,
Uh-huh.
can we go over the one that we skipped? So I have a question about that. The one with MCPVA.
But what does MCPVA do to an alkene?
We're gonna make an epoxide,
Uh-huh. And then you're going to react the epoxide with a good nucleophile?
right? I was wondering if there's any hydride shift in there.
Hydride shifts occur with carbocation.
Okay, so
This reaction is not going to have a carbocation, just like here. Do we have a carbocation anywhere?
no.
No. You got a strong nucleophile. It's going to be SN2. You're only going to get a carbocation with epoxides under acidic conditions.
Got it.
Proteate and then the oxygen. Oxygen just leaves. The oxygen's not just going to leave. It won't just leave. Okay, you still have to. For the oxygen to leave by just ionize, SN1 mechanism, just leave. It ain't going to do that unless you're protonated.
Got it.
What it will do, what is unique is you can make it leave by an SN2. A strong nucleophile will kick it off without having to be protonated. So all of our strong nucleophile reactions are SN2. Forcing it off. Backside attack. Terbutaline. We can back this up to, okay, how can you make terbutaline? Now, the direction said to start with an alkene. Let's ignore that for a minute. What reaction could you do? We can back this up to, that's just the aromatic ring there with the phenols. Let's just save some ink there. Boom, boom. We have this terbutylamine. What if I back it up to that there? If you had this, could you prepare terbutaline from that? How would you do it?
I would back it up to an epoxide.
We could back up to other things. Before we do that, though, how about if we backed up to this? How could you make terbutaline this way? That is this a viable retrosynthetic approach? What would you react this with to get terbutaline? Yeah, like KOH or something. KOH could be a nucleophile. Just do an SN2 and kick off the bromine. Everybody see that? That's analogous to a Williamson ether synthesis, except we're not using an alcohol, we're using the simplest oxygen anion. SN2? Well, how would you make this? Well, there could be a variety of ways, but you don't want to get into an endless loop where you say, hey, I'll take the alcohol and, back it up to that, and then how would you make that from the alcohol? And if you're confused, that's okay, because I'll look. How would you make this? How would you make that from the alcohol? Maybe PBr3. It is a secondary alcohol. Perhaps just HBr may work. Old classical propionate, and then. Sure, it's basic, but guess what? PBr3 is also a Lewis acid. I mean, if you're concerned about amine reacting, you should also be concerned with PBr3. Yes, and this is all possible. But here's the thing: is why would we convert the alcohol to the bromide and then convert the bromide back to the alcohol? You got to be careful. You get in the dangerous loop of this doesn't make any sense. All right. The other thing is, usually when you do synthesis, it's best to go from small fragments and build up larger. Now we may not do that here, but instead of backing up to the bromide, what else could we do? Well, let's back up to what?
Oxide and Sure.
Oxide alkene.
I'm back up to an epoxide?
Yes.
Mhm.
Well, we could try that. Here's the aromatic ring with the phenols. What epoxide though? Boom, boom. That right there?
Mhm.
And back that up to an alkene.
And we can back this up to an alkene. Because we know how, okay? Sure, this is pretty simple. How do you make epoxides? Alkene. So we react the alkene with what?
MCPPA.
Some type of peroxy acid. MCPPA is most common. We get the epoxide and we react that with what?
Tert butyl amine.
Yeah.
Some,
Called terbutylamine. Yeah. Why does that work? Well, how do we know to back that up to the epoxide, that epoxide? Because we recognize that we have a carbon-carbon OH. And could this here be a nucleophile?
Yes.
To add to a carbon, okay, yes, that's what you're going to have to see here. And so you back it up. You basically, it's like, okay, the oxygen comes back in and makes the ring and kicks off the nucleophile, and you're thinking. But here, these electrons come in here, attack here. Would it attack this carbon, or would it attack the other one?
The one on the right.
This one, least substituted. Kick off the oxygen. And I'm going to show, okay, that's just sort of the reaction. And then what type of step do we need sort of in our mechanism after the initial nucleophilic attack?
Proton transfer.
Yes, we need H plus transfer. Good. So I'm going to say with H plus transfer. Now in an actual, we don't actually need to show this. That's going to happen. I'm just showing it to clarify that that's happening. If we were to show this, you could just show one arrow here. Yes, that's going to react to this to give that. Proton transfer would just take place there. And so there's a synthesis from smaller, well, it ain't really small in terms of carbons, is it? Not really, but backing up to the bromide really doesn't do much for us. Because I don't know how to back up from there unless we do something that we've never talked about. But there you go. There's a use of epoxides, recognizing how you can do a retrosynthesis. Nucleophile, carbon-carbon OH, we recognize that. And then we can design our synthesis. We looked at epoxy glues. I mentioned in Organic 1 a little bit about mustard gases, okay? Very dangerous molecule there, used as a war gas in like World War I. It is yellow, which is why it was called mustard gas. Very easily, okay, just a little heat or just let it get out of the house or something, it'll just do this naturally. It'll just break apart. A little light energy or a little energy. Got an internal nucleophile, but what do we form here? Look at that right there. Actually, I'm sorry, I did it on the other end. You do it on the other end too. Do it on the other end, what are we forming here?
epoxy.
It looks like an epoxide, but it's a sulfur. So I'm calling it a thioepoxide. But not only is it just sulfur, the sulfur has a positive charge. Great leaving group, positive charge. Lots of ring strain. This here is a very reactive electrophile. Nucleophiles are going to come in here and kick off that sulfur very easily. And your body has all types of nucleophiles. DNA, okay? But water. You got water all everywhere in your lungs, vapor, okay? Trust me, yes, water. And water can come in and do that, but we're going to produce HCl if you look at the mechanism. And HCl in your lungs is just going to kill your lungs. Okay? There's so many things that can go wrong with that. You're basically breathing in HCl. Bad stuff. But understand the chemistry there. There's a molecule. They're feeding it to the cows to make them grow big, but these things are starting to fall out of favor. Nucleophile carbon OH. All right. So now when you look at molecules, you're going to be looking for nucleophile carbon OH, right? And saying, hey, I can make that from an epoxide. Right, that's what we're doing. You can take a look at that, but let's look over here, some more synthesis. Okay, these would be standard type of synthesis questions you'll see from me. The top one, we haven't seen that yet. Let's look at the second one. Provide a synthesis of this compound starting with what?
Bromobenzene.
From bromobenzene. That's the direction. Well, we got the benzene here. What type of functional group do we see here?
Ether.
Ether. Okay, let's check our toolbox. How do you make ethers?
Williamson. Yeah.
Williamson ether synthesis. Classical way, most direct, easiest way. Can we back this up to what? To what Williamson ether synthesis? We can cleave on this side or this side.
The right side.
Well, let's go right side and back that up with what? O minus plus what?
Like CHI.
Plus ethane?
Yes.
No.
You need a
And
Maybe.
the alkyl halide.
Will these two react to give that?
No, you have to.
Alkyl halide.
No, this is inert. We need a leaving group on here, right?
Like,
What's your favorite leaving group?
Iodine.
Okay. How about this? Will this work? Yes. There you go. That's just a good old SN2.
Form epoxide and Grignard reaction.
How are you going to make this anion? Well, this is pretty straightforward, isn't it? From the alcohol, right? Back it up to the alcohol, and you're coming forward, you react this with what? Sodium or sodium hydride,
Yeah.
right? We talked about that. Okay, so that is, if we had this alcohol, we know how to make the final product, right? So now the job becomes, well, how do you make the alcohol?
You,
We're gonna need magnesium.
We're going to need magnesium.
Grignard reaction.
I see something carbon OH. I'm going to back this up to,
Epoxide.
can that be a nucleophile?
Yes.
Well, any carbon group could be a nucleophile, be like Grignard. Yes, powerful Grignard. That's why Grignard won the Nobel Prize. Back this up to maybe that Grignard plus what? All we have is two carbons. Basically, think about this, the oxygen coming in here and kicking back off the nucleophile. Now, that ain't going to happen in real life, because this ain't a leaving group. But we can do that and say, okay, we can make that bond there, plus just the simplest epoxide. Would these two react to give that alcohol?
It would have another step, it would have like a workup to it.
You're going to have to put the proton on, yes. This is basically anion, right? We talked about these. It reacts as if it's that. Now, in real life, it's a little bit complex. It may not be a free anion, but for us, it's a free anion. Just reacts like that. This comes in. Either carbon is the same thing. Kick that off. Okay? You will have to bring in a proton. All right? You're going to have to add in some acid or something because this is going to be O minus. Let's get a little innovative though. What if you didn't bring in the proton? What would the product just be if there was no proton added, no workup? What would it be?
It would just be in the one
An
step for
alkoxide.
moving to the third.
What would it be?
An
And
alkoxide?
Okay, which is,
Yeah.
so possibly we could add this, and instead of adding H plus workup,
You just go straight to the.
let's add ethyl iodide. Because why put the proton on and then turn around and take it back off?
It's waste of material.
Do what?
It's a waste of material.
I'm just showing you that perhaps what we did here is we put the proton on and then hydride took it back off. I'm just showing you a little sort of sneaky thing here that we could have just not put the proton on. Instead of, we could have just added an ethyl iodide and put that on. That would have, all right? Now most books are going to show you stepwise and whatnot. Okay. Now the ones below ask you to start with styrene. Okay, this is its common name, styrene. And you can polymerize styrene. And you're going to get,
Styrofoam?
yeah, it's called styrofoam. I was going to say you get polystyrene. But polystyrene is more commonly known as styrofoam. Because you blow air through it, it will kind of expand a little bit and it's styrofoam. So when you drink the styrofoam cup, it's polymer of styrene. Okay, there's others for you to do. We need to make some progress, particularly the acid. Because how do you make carboxylic acids? You have that reaction in your toolbox.
With protein.
You didn't have me for Organic 1. That is, you covered that in Organic 1. I don't cover those analysis in Organic 1. I cover it here. We're about to do it.
Oxidation balls?
So a couple of you have already seen those analyses.
CR.
Basically, what I'm getting at is we've never looked at how to make carboxylic acids before. So you're not going to be able to do the top one yet. At the next handout, we will see synthesis of some carboxylic acid. Okay? We'll look at alcohol oxidations. But we'll also look at alkene oxidations. And I don't cover these reactions in Organic 1. There's a couple of reactions, okay, that some of you may have already seen before. Oxidation of alcohols. The one I gave you today. Estradiol, an estrogen. Look at this alcohol here. It's undergoing a reaction and becoming a ketone. Carbon-oxygen bond. It's still carbon-oxygen, but now it's a double bond, carbon double bond oxygen. And it lost the H. It's now carbonyl. Specifically a ketone. This is a standard oxidation of an alcohol. Okay? Oxidation of the alcohol. Why is it an oxidation? In Gen Chem, you did redox and you looked at oxidation states. Iron 2 going to iron 3 is an oxidation. All right? The other way would be a reduction. All right? How do we know this is an oxidation?
Because you're losing a proton? Or no way?
Another way in organic chemistry, and we may have seen this in Organic 1, is number of bonds to a more electronegative atom. How many bonds to a more electronegative atom does carbon have?
That carbon,
The carbon. How many bonds to a more electronegative atom?
one.
One.
One bond to the oxygen. How many bonds to a more electronegative atom over the right?
Two.
2. That's an oxidation. Increasing the number of bonds to a more electronegative atom. On the other hand, if you eliminate or reduce the number of bonds to a more electronegative atom, that's known as a reduction. Okay? And so this way is an oxidation, but if we go this way, that's a reduction. All right? Now there's one other way to judge redox in organic chemistry. That's number of H's. And while it could possibly work here, it doesn't work cleanly here. We'll mention that later, okay? Now some books may say more bonds to oxygen, right? 1 bond to oxygen, 2 bonds to oxygen, more bonds to oxygen is an oxidation. Yes. That's a little bit narrowly defined though. Just consider oxygen a more electronegative atom. That way you know you can do much more than just dealing with oxygen. Expands it out and makes it more applicable. Okay, so there's some warm-up stuff. Alcohols undergo oxidation. This is shown a couple of different places. Look here. A primary alcohol. This is generic for oxidation. Sometimes O, sometimes OX. Oxidized. We get the aldehyde. Now I've turned the oxygen up. Okay. But basically what we're doing here is we're creating a double bond between the C and the O. Double bond between C and the O. And we do also lose the H, so it's no longer a protic function. Now one thing about aldehydes is they're susceptible to further oxidation. If you have water around, further oxidation of aldehyde gives a carboxylic acid. Carbon has 1 bond to oxygen. Carbon has 2 bonds to oxygen. Carbon now has 3 bonds to oxygen. More oxidized. But here, we're actually adding an oxygen. That has to come from water. Okay? First oxidation, we didn't add any oxygen. Okay, secondary alcohols oxidize to the carbonyl compounds just like that. But it's going to be a ketone, of course, because you got 2 R groups. Where here you only had 1 R group. The other H on this carbon remain. I'm just drawing it in there, aldehyde. Ketones are not susceptible to further oxidation in this class. There is some advanced chemistry where you can oxidize them, but it's odd advanced. We're not going to look at it. For us, ketones are not further oxidized. Tertiary alcohols, you cannot oxidize them in this class. Basically, in these oxidations, you're removing an H from the carbon. There's an H loss there, there's an H loss there. There's no H to lose here. And we can't make a double bond to oxygen because then you'd have 5 bonds to carbon. The only way to make a double bond here is to lose one of these R groups. And you're not going to do that very easily It has to be something very odd, not this class. Okay? What type of reagents will do this oxidation? I assume you can see this here. It's a little dim if you can't. Please, Jill. Okay, we have two different handouts here. It's sort of itemized here, listed here. This is kind of the outline. The other page, what color is it?
Blue. Blue.
Yeah, I thought I had it right here. Thank you. Big three. I call them the big three. Big three are the most common oxidants for oxidizing alcohols like this. What are the big three? They're all oxidants. And they have heavy metals, okay? Potassium permanganate. Hopefully you saw some of these in Gen Chem. They also have oxygen, which sort of indicates, like, hey, I'm an oxidant. Okay? Chromium trioxide. Sodium dichromate. Dichromate. 2 chromium. Now the sodium could also be like potassium dichromate. Both are very common. But I consider it the same thing. Okay? These will do those reactions we just looked at very easily. Now, a little bit of information here. These two, when treated with aqueous acid, which you usually do, for example, you might do chromium trioxide and sulfuric acid. Acetic acid also works, maybe a little aqueous, okay, like aqueous acetic acid or something. Aqueous acid, these two are converted to chromic acid. Both of them are. And with those two, chromic acid is actually the oxidant. If that was a sulfur, that would be sulfuric acid. So its structure is very like sulfuric acid. Now, chromic acid is orange, and the chromium, hopefully you'll be able to do this, but the oxidation state of the chromium is +6. Yeah.
Say the chromium, this compound is orange color?
Yes.
Is that why when you see things rust, they're orange?
When you do what?
Is that when you see rusting oxidation off metal? It's
No, that's because the iron is being converted to iron oxide, and iron oxide is orange or rust colored. Yeah. No, the oxygen is the oxidant there. Iron is being oxidized. Okay, there you go. Chromium 6 is orange. Here's your alcohol, of course, primary or secondary, because tertiary alcohols don't do any of this, right? Tertiary alcohols won't react with an oxidant. It's converted to a carbonyl compound, right? The chromic acid, I'm not going to give you full details, but the chromium 6 is converted to chromium 3. That seems like a 3-electron oxidation. It's actually only 2. It's actually first converted to chromium 4. The chromium 4 undergoes sort of some type of autocatalytic process, and it jumps down to chromium 3, which is more stable. All right, so I'm leaving some of it out. The important thing is, that's now blue. And you have a visual evidence that this reaction is working. All right? And it actually is used as an unknown test. Because I got an alcohol here. Is it primary or tertiary? Or either?
either.
We could react it with chromic acid and add in some orange. What if I add in orange and all of a sudden my reaction turns blue? That means the oxidation chemistry took place. The alcohol reduced the chromium, but the alcohol got oxidized. What type of alcohols will turn orange to blue?
Primary.
Only primary and secondary. A tertiary will not do this. There's no reaction. Your orange is just going to sit there. So if I add an orange and it just stays orange, it must be what? You got to be careful. It might be tertiary, or it might just be something else that doesn't react. But what it is not is a primary or secondary, because those should turn orange to blue. By the way, breathalyzer test. Okay? I've never had to use one of these or anything, but you blow in it. What they're really looking for is how much orange are you turning blue? Ethanol is a primary alcohol. You got a lot of primary alcohol in your breath, and you blow in it, you're going to turn a lot of the orange blue, and then you're going to have a free night stay at the Gray Bar Motel. Okay? Because they have a little light, they're doing spectroscopy there, and they're seeing how much blue is generated from your breath. Okay? So you don't want to create any blue when you blow into it. All right? Because the more ethanol you have, the more you're going to convert this to blue. And so, spectrophotometry. Okay? All right. Now that test is called a Jones oxidation test. It's our second alcohol test. What was our other alcohol test? Lucas, and it told you what?
If it was
It also, okay.
but it doesn't reduce.
Well, just know your two tests there. Okay. Those are called wet chemical tests. Wet because they're reagents that are liquid-based, or IR. You don't call that a wet chemical test. That's a spectral analysis. Okay. So for example, below, if we take this alcohol, now this is kind of two different places. Yeah. Okay. I thought there was something else here. Oh, I know where it is. It's the third place, but I'm missing the brackets. Remember the green outline?
Mm-hmm.
Yeah. I should sort of... It is shown on the green outline here. Alcohol. One of the big three, yeah. Aldehyde. But with the big three, you cannot stop at the aldehyde. The aldehyde gets further oxidized to the carboxylic acid. And brackets here typically means that you're not stopping there and it cannot be isolated. But it is sort of an intermediate. And the reaction just continues. With the big three, you go all the way to a carboxylic acid. If you wanted to stop at the aldehyde, you'd have to use another oxidizer. It's called PCC. Or these variations. Some older textbooks have this. You could look at that. It's just a slight variation. You can stop at the aldehyde if you use those. And of course, the aldehyde can be further oxidized. One of the big three will do that, or toluenes. Okay. We're about out of time, though, but just to set the stage here, the PCC is shown over here. Okay. Toluenes. Basically, we'll pull this together on Wednesday. We'll also look at a brief mechanism for how the oxidation takes place. It'll be brief, just so it's not so much magic. Then we'll be moving into the oxidations of alkenes, which is also in these handouts. Okay, including ozonolysis, things like that you probably saw
that I don't do organic one, because I think we do enough already. Do that here.